Hey everyone! Welcome back to our channel where we make chemistry fun and easy to understand. Today we have an exciting topic lined up for you. Ready to explore something cool? We're going to dive deep into the fascinating world of coordination compounds. These are special types of chemicals that play crucial roles in various biological and industrial processes. So, what exactly are coordination compounds? Simply put, they are complex molecules where a central metal atom is bonded to surrounding molecules or ions, called ligands. These bonds are not your typical ionic or covalent bonds but are a bit more special. Don't worry, it's not as hard as it sounds. We'll break it down for you. Imagine the central metal atom as a celebrity surrounded by fans, the ligands. The way they interact is what makes coordination compounds so unique and interesting. We'll go through this step by step, and you'll see why understanding these compounds is crucial, especially if you're preparing for competitive exams like NEET and JEE. Knowing about coordination compounds can give you an edge in your chemistry exams. These compounds are everywhere, from the green stuff in plants, known as chlorophyll, to the hemoglobin in your blood that carries oxygen. They are also used in various industrial applications, including catalysis and material science. Let's unlock the secrets of these amazing chemicals. By the end of this video, you'll have a solid understanding of what coordination compounds are, how they function, and why they are so important in both nature and industry. So, stay tuned and let's get started. So, what exactly are coordination compounds? These fascinating structures are a cornerstone of modern chemistry, playing crucial roles in various fields from medicine to material science. Imagine a metal ion, like a king, in the center of a bustling kingdom. This central metal ion is surrounded by a host of other molecules or ions known as ligands, which act like loyal subjects or helpers. These ligands are not just randomly floating around, they are strategically positioned around the metal ion, creating a stable and unique structure. The metal ion with its positive charge attracts these ligands, which can be neutral or negatively charged. Think of the metal ion as a king, and the ligands as helpers. These helpers can be tiny particles or larger molecules, each bringing its own unique properties to the compound. They attach themselves to the metal ion through a process called coordination, forming a coordination complex. This coordination process is like a dance, where each ligand finds its place around the metal ion, creating a harmonious and stable structure. The resulting coordination compound has properties that are different from the individual components. To visualize this, think of the solar system. The metal ion is like the sun, and the ligands are like the planets orbiting around it. Just as the planets are held in their orbits by the sun's gravity, the ligands are held in place by the metal ion's charge. This solar system-like arrangement gives coordination compounds their unique characteristics. The metal ion and ligands work together to create a structure that can have special chemical and physical properties. These unique properties make coordination compounds incredibly useful in various applications. For example, they are used in catalysis to speed up chemical reactions, in medicine for imaging and treatment, and in material science to create new materials with specific properties. Understanding coordination compounds opens up a world of possibilities in science and technology. Let's meet the stars of the show: metal ions and ligands. These fascinating entities play a crucial role in the world of chemistry, particularly in the formation of complex compounds. Metal ions are essentially atoms that have lost one or more electrons, giving them a positive charge. This positive charge makes them highly reactive and eager to form bonds with other atoms or molecules. Ligands, on the other hand, are atoms, ions, or molecules that can donate a pair of electrons to the metal ion, forming a coordinate bond. Together they create a stable structure known as a coordination complex. Metal ions like iron or copper have a positive charge and are at the center. These metal ions are often found in various oxidation states, which means they can have different charges depending on the number of electrons they have lost. For instance, iron can exist as Fe2+ or Fe3+, while copper can be found as Cu+ or Cu2+. These different oxidation states allow metal ions to participate in a wide range of chemical reactions, making them incredibly versatile and important in both biological and industrial processes. They're like the team captain. Just as a team captain leads and coordinates the efforts of the team members, metal ions direct the formation and stability of the coordination complex. The metal ion's positive charge attracts the ligands, which are like the team members, to come together and form a cohesive unit. This analogy helps us understand the central role that metal ions play in the structure and function of coordination complexes. Ligands are the team members. They come in various shapes and sizes, each with its own unique properties. Some ligands are small and simple, like water or ammonia, while others are larger and more complex, like ethyllenediamine or porphyrins. Regardless of their size or complexity, all ligands share the common feature of having at least one pair of electrons that they can donate to the metal ion. This donation of electrons is what allows the ligand to form a coordinate bond with the metal ion, creating a stable and functional coordination complex. They can be molecules like water or ammonia, or ions like chloride. Each type of ligand brings its own unique set of properties to the coordination complex. For example, water is a neutral ligand, meaning it does not carry a charge, while chloride is a negatively charged ligand. The nature of the ligands can influence the overall properties of the coordination complex, such as its solubility, reactivity, and stability. This diversity of ligands allows for a wide range of coordination complexes to be formed, each with its own specific set of characteristics and functions. Each ligand has a pair of electrons it uses to connect with the metal ion. This pair of electrons is known as a lone pair, and it is what allows the ligand to form a coordinate bond with the metal ion. The strength of this bond can vary depending on the nature of the ligand and the metal ion, but it is generally quite strong and stable. This stability is what allows coordination complexes to perform a wide range of functions in both biological and industrial processes, from catalyzing chemical reactions to transporting oxygen in the blood. For example, in Fe-CN6-4, iron is the captain, and cyanide is the team. This particular coordination complex is known as hexacyanoferrate, S2, and it is a classic example of how metal ions and ligands can come together to form a stable and functional structure. In this complex, the iron ion is in the +2 oxidation state, and it is surrounded by 6 cyanide ligands. Each cyanide ligand donates a pair of electrons to the iron ion, forming a strong and stable coordinate bond. This arrangement allows the complex to perform a variety of functions, from catalyzing chemical reactions to serving as a building block for more complex structures. The 6 tells us there are 6 cyanide players on the team. This number, known as the coordination number, indicates the number of ligands that are bonded to the central metal ion. In the case of hexacyanoferrate 2, the coordination number is 6, meaning there are 6 cyanide ligands bonded to the iron ion. This arrangement is quite common in coordination chemistry, and it helps to illustrate the central role that metal ions and ligands play in the formation and function of coordination complexes. By understanding the interactions between metal ions and ligands, we can gain a deeper appreciation for the complexity and beauty of the chemical world. Naming these compounds is like learning a secret code. Once you know the code, it's easy. First, find the ligands and count them. In QNH342+, we have 4 ammonia ligands. Next, name them. 4 ammonia ligands are called tetraamine. Then name the metal ion. If it's negative, use the fancy name, like ferrate for iron. Finally, add the metal's charge in Roman numerals. So, QNH342+ is tetraamine copper 2 ion. Coordination compounds can be neutral or ionic, meaning they have no charge or a charge. Neutral ones, like nickel tetracarbonyl, have no overall charge. Everything balances out. Ionic ones have a positive or negative charge. Tetraamine copper desiccant is positive, while hexacyanoferrate 4 is negative. This charge is important for how they behave. These compounds aren't flat, they have 3D shapes. The shape depends on how many ligands are attached to the metal, called the coordination number. 2 ligands make a line, 4 can make a pyramid or a square, 6 often make an octahedron. Seeing these shapes helps us understand how they react. Coordination compounds are everywhere. In biology, hemoglobin, which carries oxygen in your blood, has iron. Chlorophyll, which helps plants make food, has magnesium. They're also used in factories to speed up reactions and in medicine for things like cancer treatment. Want to ace your NEET and JEE exams? Here's how: understand the basics, like coordinate bonds and ligands. Practice naming them. Use models to see their 3D shapes, and solve past exam papers. Coordination compounds are cool and important. By understanding them, you'll be ready for your exams. Stay focused, practice, and ask for help if you need it. You got this.